Hello, everyone. Good morning and welcome to the last session of the Reinforcement Learning Bootcamp. And now I hand over charge to Gaurav.
Thanks, Jatin. Okay, so we are on to the last day of the bootcamp. And so today I'm going to talk about computational RL, or how do you design compute efficient RL algorithms. Okay, I was just telling this, Jatin, I've been writing a lot, but maybe it will be easier if I wrote some of the slides a priori. So it's going to fast things up a little bit. Okay, so when do we actually say that a problem can be solved efficiently, right? Like, is when the time that you take to solve the problem is some kind of polynomial of time that you need to read the input. Okay, so for example, if you're doing sorting, right? If you're given n numbers, you need n time to read those numbers. And then, we'll consider it efficient if the time to sort is less than like some kind of polynomial in n. And we know we have an n log n algorithm, right? So or like at best it takes n squared, right? So we can always do sorting efficiently. Okay, similarly, primality, if I give you a number n, you only need log n bits to represent that number. And so we would like to check primality in like poly log n time. Okay, and so a KS primality algorithm does that. It's a big result, right? So but we can do both of these things in polynomial time. And what polynomial time changes based on the problem, right? Because sorting takes n time to read, and like primality takes log n in whatever like n is, right? Okay, so we're going to look at two computational problems. One is going to be a problem called SAT, and another is the problem that I'm going to build out of RL. So I'm going to call it, say, linear RL. Okay, so let me quickly go over what SAT is. Okay, so for SAT, you're given a Boolean formula. Okay, so Boolean formula is composed of variables. So you have x1 to xn or xv, right, to xv, right? And they're all variables which can be assigned either 0 or 1. Okay, and to design a formula, you have like these small operators. You can either do a not operator on a variable. So, x1 not is, if x1 is 1, then x1 not is 0. And then you have an OR operation, which allows you to kind of correlate variables or entangle them. So x1 or x2 is 1 only when both of them are 1, or one of them is 1. And also kind of entangles them, and this returns 1 if both of them are 1. So it's a projector over a subspace, right? And so Boolean formula is composed of clauses like this. That's what I'm going to look at, the CNF. So you have a clause where x1 is ORed with x2 with x3 is the clause, and then I have multiple clauses in an AND. And usually what I want is like I want to find an assignment which satisfies all these clauses, right? Or satisfies the Boolean formula. So for that, it has to satisfy all the clauses. Okay, so using that, we can define a SAT problem. Okay, a SAT problem on V variables. So there's going to be like some way to scale up or down a problem. Okay, so for a SAT on V variables, we're given access, as input, a Boolean formula. Okay, say psi. Okay, on V variables. Let me just move it here. And polynomial in V many clauses. Okay, and then the something less than whatever. And the goal is to decide if there exists some assignment which satisfies this Boolean formula. So this means is like you're given x1, you assign it 0, say x2 goes to 1, some assignment which satisfies or such that phi of x is 1. It's possible maybe none exist, and that's what you're going to figure out. Okay, so that's the SAT problem. Okay, and we are looking for algorithms for this problem. And usually, when people talk about SAT algorithms, they're looking at deterministic algorithms. But people have also been looking at randomized algorithms. And so that's what we'll care about. Okay, so what's a randomized algorithm? Okay, we say, an algorithm A solves SAT in time t with probability p if A runs in time t. Okay, and returns yes on positive instances. Positive as in you can solve SAT with probability greater than p. And no on negative instances with probability 1. So it's like a one-sided error. If your Boolean formula is not satisfiable, then you have to say no. But if it's satisfiable, then sometimes you can make mistakes. A constant fraction many times. That's the randomized algorithm we'll be looking at. Okay, and if you know a little bit, then SAT is really the canonical NP-complete problem. Okay, and so there are two computational facts about it that we'll use. So first of all, because NP-complete, right? So unless NP is RP, there are no randomized polynomial time algorithms for SAT. So no randomized algorithm. So according to the definition I just defined above, can solve SAT on V variables in time poly V with probability greater than 9/10. Okay, that's just because how NP and RP are defined. And okay, so that's already a pretty strong computational statement. But we can make it stronger, right? So all the SAT algorithms we have right now, they are, not even like, sub-exponential, right? They're not even like quasi-polynomial. So, so the best set algorithm we know still takes actually like strictly like exponential time, right? So, so you can use that fact. So people have been looking at certain hypotheses. So one of them is the randomized exponential time hypothesis. Okay, I should know the citation, I guess, but I forgot. But Russell was one of them. And so this hypothesis basically says that there exist constant C such that no randomized algorithm can decide SAT with V variables in time 2 to the CV with probability 9/10. Okay, so there's this fixed constant, and you cannot do better than that. Uh, okay, so that's SAT. Okay, so SAT is hard in like very, very, strict sense. Like it's actually really hard. So, so now we're going to look at our second problem, the linear RL problem. Okay, actually, are there any questions about SAT quickly? Maybe take.
No.
Okay, perfect, perfect. Today we need all the time we can get. Okay, so I'm going to define the linear RL problem. Okay, so, I'm going to define this a little bit slowly, right? But it's exactly what you would expect the linear RL problem to be. This is what we have been talking about, but we have to write this a little bit formally, unfortunately, or fortunately. Okay, so in linear RL problem, you're given access to a MDP, okay, with, some state space S. And action space A. Okay, and right away I'm just gonna assume like A is like 2. So it's a very small state space. Okay, so I'm making the problem easier in some sense, right? So computationally, this problem should be even easier than where like actions could be larger. Okay, and so what do I mean by access to an MDP? And that's really what we want to focus on most, is we have access to the oracles. So one of them is a reward oracle. Okay, so this oracle, if you give it a state S and an action A, it gives you a sample from the reward function RSA, which is a stochastic function, right? Or a randomized function, right? And another thing is this oracle for transition function, which given a state and action gives you a sample from the transition function. And actually, what happens is I can even assume this is deterministic. So you don't get your transition function is deterministic. So you don't get a sample from some distribution. It's actually just a single state. So that makes the problem really like somewhat simpler, right? It's kind of saying in the chess, the opposition can only play like deterministic strategies. They cannot play randomized strategies. And I guess that makes the problem a little bit easier, right? And so, but I guess maybe not in chess. Okay, but that's still pretty, yeah, this should be a pretty easy problem now. Okay, also because maybe this is, if you assume that rewards are also deterministic, then you have basically a linear time algorithm for solving this problem. So really, like this one change kind of moves it from being a polynomial time solvable to having exponential time hardness. Okay, so let me just remark here. If RSA is deterministic, then this problem is polynomial time solvable. Actually, linear time solvable. Okay, and it's actually just turns out to be just Gaussian elimination, really. Okay, so second assumption we're gonna make is that there exist nice features okay, for all states and actions. Okay, such that there is some unknown theta star in RD. So I'm going to say, maybe I should be explicit here. I'm going to say there exist nice features in D dimension, or maybe D dimensional. This is nice. D dimensional features. Yeah, that's probably nicer. If there exists a theta star such that V star of S is linear in psi of S. Okay, and W star in RD such that Q star of SA is W star psi S comma for all SA in the product space. Okay, and these are unknown. And they have norm bounds that less than norm one. Okay, features also have norm bounds, but I'm not writing those. Okay, and so one more thing we need here is how to actually access these features. Okay, so we need a feature oracle. Okay, which, given state tells you psi of S, and given a state action pair gives you psi S comma A. Okay, so anytime you want any of these feature vectors, you just ask this feature oracle for it. You actually don't even need to be in the state. So that makes the problem like a whole lot easier, actually. Okay, so with that, I'm going to define formally, what is linear RL problem. So linear RL, with d-dimensional features, d-dimensional nice features. Okay, so d is the parameter that we can scale in this problem, just like number of variables was the parameter we could scale for making SAT hard. Okay, and maybe, add even like with H horizon. Yeah. Okay, so in this problem, you're given input or access to input. So you're given access to an MTP, which means a reward oracle, a transition oracle, feature oracle. So access to these oracles. And the features are in RD. And we assume the number of actions, are less than or equal to 2. Horizon is polynomial indeed. And V star of S0 is something between 0 and 1. Okay, so, it could be something big. It doesn't really matter. But for simplicity, let's just keep it bounded. Okay, and then the goal is to find a policy pi such that V pi S0 is bigger than, let's make it strict, V star S0 minus 1/4. So if it's 0, you can return 0. But if it's 1, then you should return at least 3/4. Okay. So this is the linear RL problem. Any questions about the problem? And this will be a perfect place to ask questions.
Very clear. So thanks. We can continue.
Okay, awesome. Okay, so I'm going to show 2 theorems about this problem. So the first one is no polynomial time. So basically, unless NP is RP, there are no randomized algorithm to solve near linear RL with d-dimensional features. In time, poly D, okay, maybe I'll say H with probability and horizon H. Okay, so you cannot solve unless NP is RP, there are no randomized algorithms to solve this problem with probability more than 9/10. Okay, and the second thing we can show, but I won't have time to show that, is exponential lower bound. Which says that under RETH, which is the randomized exponential time hypothesis. So unless NP is RP, the best you could probably prove is something like SAT, right? There's no polynomial time. But under ER, ETH, you should be able to prove exponential lower bound. So what we are showing is a slightly weaker thing. So there is no randomized algorithm to solve linear thing with D dimensions, H horizon in time exponential of minimum of D1/4, H1/4 with probability 9/10. Okay, so you are going to pay exponential. And I mean, we can, maybe talk about like we can improve this too and kind of match some upper bounds. Oh, sorry, yeah, but okay. Any questions? Otherwise, I can go at the proof.
Questions? Yeah, thanks. Very good. We can go to the proof.
Okay, perfect. Okay, so now I'm gonna sketch this proof a little because there's gonna be, a lot of formal arguments that I don't want to get into. But before I do that, I just want to say like there are other computational results in RL2. For example, there is a upper bound showing that if you have a linear MDP where the transitions are linear, then you have a polynomial time algorithm, right? So, but transitional linear is like a really strong thing because it means like every policy's values are linear, like not just optimal, and also like you take any function and you look at like Bellman, update from like Q to V, then pick any function and do this update and you are gonna get a linear function. So it's a really like strong. And so we don't know if any of the settings satisfy this, but it's a good result. It's kind of stays like, there is some like computational easiness if you go making a problem easy and easy. Very soon, there's a way to make it computationally easy. And in terms of lower bound, this was like the first one, I guess. Before there were like other results, but like in function approximation. But then there's a lot more new computational results by Golovich, Moitra, and Rohadki. And so, they have a lot of good results in computational RL now. So, okay. So now I'm going to show you the proof sketch. Okay, and so the way I'm going to show lower bounds for linear RL is, by kind of relating it to SAT. So our goal will be like if somebody gives me a Boolean formula, which is like a SAT instance, right? I would like to like transform that into an instance for RL, which is, so, Boolean formula, say x psi from like x1 to xv. So it's on v variables. And I will want to turn it into an MDP, with state space 0, 1 to v. Transition function TSA that I'm going to build from it. I would need to build a reward function from it. Features. Okay, and then I'm constrained in the form that, my V star and Q star have to be linear in these features too. Okay. And so, okay, so the thing that I'm trying to do is like, I want to turn an algorithm for linear RL into an algorithm for solving SAT. Okay, so what it means is like if I can design an efficient RL algorithm, then basically I can do this transformation, run my RL algorithm on it, and use that solution to solve SAT. So basically, kind of this transformation of RL algorithms to solving SAT. Okay, so to achieve, you know, qualitatively that makes sense, but like quantitatively, like if I want to turn a polynomial time RL algorithm to polynomial time SAT algorithm, right? I need this reduction to also happen efficiently. So, so there are like two like computational challenges here, and I would consider them like the main challenges. Um, is to, we're restricted for this feature dimension, which is this, this D. We want this to be something which is polynomial V. It cannot be bigger than polynomial. Because when I'm kind of simulating my MDP, if somebody asks me, and I'm these oracles, if somebody asks me, okay, what's your state? I have to write down, my next state, or the transition function, and I have to give out like features, and features I have to write down the features, and those numbers should also be like, written in poly D time, poly V time. And the simulation of this transition and reward function should also not take more than like polynomial time. So this should also take like poly V to simulate. Right? When I'm say there is some way of describing this transition function and reward function, but I have to design algorithms for them too, right? So if somebody says, you have to compute this thing to do reward function, I have to figure out how long it's going to take me to compute that. Okay, so these functions should also be like computable, or these are randomized functions, like, or at least a reward function is. So that should be, I should not take more than poly V time to simulate that. Okay, and if I can do all these things, then yes, what I can take, an RL algorithm, and I can use it to solve a SAT problem. Okay, which basically, or I can turn it into a SAT algorithm. And that means that basically RL is at least as hard as SAT. Okay, and so that is what we want to prove. Okay, so our goal now is going to be, how do we, given a Boolean formula, turn it into an MDP? And it's such that, the transition and reward function don't seem too complicated. Like you have good out, you feel like you can figure out how to do reward function, and my feature dimensions are not big. Okay, so I'm gonna start with like a toy construction. No. Okay. Okay, it's a construction which takes in a Boolean formula and turns it into an MDP. Okay, and so this construction, the way it works, so MDPs are games, right? So so this is going to be a game where we are searching on a hypercube. We're searching for a vertex. So it's gonna be like some hypercube. You are someplace and you're searching for a vertex, and so you can probably go, in all these three directions. And the way you choose which direction to go, that signal that comes from reward function. Okay, it tells you like, oh, which direction to go to find the vertex that you're looking for. Okay, so that's the basic thing, but like I'm gonna do it more formally. So to kind of explain it, let's pick a Boolean formula. Okay, I just realized the symbol I'm using for Boolean formula and features is the same. So hopefully that hasn't been confusing yet. Okay, so I have a Boolean formula. Okay, and so I'm going to turn this into a state space. So, like I said, the state space is this hypercube. Okay, in terms of like this Boolean formula, it's the assignments to these variables. So it's assignments 0, 1, 2. So that's our state space. Our action space, like I said before, it's gonna basically correspond to like flipping variables. You'll have maybe some variable in 0, you're gonna turn into 1, or 1, you're gonna turn into 0. So I'm gonna go more about what action is, it's more on it soon. But this is basically what's gonna happen. Okay, I need also a starting state, right? So starting state, the initial state, it's going to be all 0. Okay, just to make things simple. Okay, so now I'm going to define the transition function and action together. All right, it's going to make sense because it's just a game, right? So let me define transition function and what action is. So transition function takes in a state and an action and gives you some other state, and it's deterministic in my case. Okay, so what do we have? So we know one of our states, we start from all zeros. Okay, let me copy the formula. Okay, and this is the formula for which I want to write the MDP. Okay, so what's the transition function? Transition function on an action takes you from this state to another state. Okay, another state in this case is also like, an assignment. Okay, so how do I decide what action takes to what assignment? So I'm going to define a rule. It's totally arbitrary, but it's important. So to figure out what actions are available to a state, you look at what's the first unsatisfied. Okay, hold on. Thing is dying. Okay. First unsatisfied clause under assignment. Yes. So to figure out actions available at state S, you first figure out what's the first unsatisfied clause under assignment S. So for example, here under all zeros, the first one is unsatisfied, so I'm going to use this. Then my 3 actions are basically going to be the 3 variables in the clause. This is x1, x2, and x3. The actions correspond to 3 variables in clause. And basically, like if you take an action, it flips that variable. Okay, so when you take first action in this case, you'll end up with 1, 0, 0. Okay, so we have 4 variables, so I can make it very concrete. So it's actually all 4 zeros. And when I take the first action, my first bit flips. When I take the second action, second bit flips. And if you take the third action, your third bit flips. Okay, so I'm going to do one more round of it. Okay, so let's look at what are the actions available under this. 1 and then all 0. Okay, so first I find out what's the first unsatisfied clause under assignment S. Okay, so in this case, first is clause satisfied because X or X1 or X2 or X3, one of them is 1, so great. But the second one is unsatisfied. So 3 actions here. Will correspond to, X1. Oh, it's actually same. So let's do which one? Yes, let's do, yeah. Well, whatever. Okay, X2, X3. And then if you flip again, you go to 0, 0, 0, 0. And here you get 1, 1, 0, 0. You get 1, 0, 1, 0. So in this case, you flip the first one, go back to 0. In this one, you flip second. So both of them are 1. In this case, you flip third. And 1, 1. All right, and you can keep doing this. So if I chose something like this, then it will be like X flipping X1 or X3 or X4. Okay, and the not doesn't matter. Okay, so this defines, our transition function and our actions. Okay, so the only thing remaining is now reward. And reward is going to be just -1 for every action. Actually, I'm going to pause here. Is everything making sense up till now? Or because I think maybe it will be better to ask questions.
I think this was quite clear. Yeah, thanks.
Okay, perfect, perfect, perfect. I'm very proud of myself. This is, okay, great. Okay, so, and then basically the episode ends when you reach a fixed satisfying assignment. But this part doesn't really matter as much. Some S star. If there is no satisfying solution, then you're always gonna get -1. But if there is, then we fix 1. Okay, so how does this is our MDP, and we can very well, easily simulate transition function. Transition function, I was doing the simulation right away, for me to figure out what are my actions and what the action is going to do. I just have to like parse this list of clauses, and they're only poly V, many of them. So it's not so hard. Reward function is always -1. That's also not hard. So the only thing which kind of is tricky, like how does the optimal policy look like here? And is it linear, like this value function? Okay, how does the optimal policy look like? Okay, so the reward a -1 everywhere. So, you're always wanting to like finish fast, right? So the optimal policy is basically like just going towards S star as fast as possible. Okay, so what you can show, I mean, very like it would be obvious that, the best values, if you're at some assignment, the best thing you can do is just go towards S star. And because like if you're an unsatisfied clause, there's something that you can fix here in that one, right? So it basically takes like Hemingway, Heming distance between, S and S star to end the game. So you only pay minus the Hamming distance. Okay, and Hamming distance is linear in S and S star. So perfect. And Q star S comma A is, just V star of T S comma A minus 1, right? Because either you end up on a satisfying solution, in which case you end, there are no actions, or otherwise just minus 1. So it's linear. So both Q star and V star are linear. I mean, I haven't given you features, but I'm not gonna do that because this is not gonna like work out. But at least we know like they're linear, so and also like it's believable. Okay, so everything works out except that, this problem has infinite horizon. And for infinite horizon makes sense. Why can't we solve it in polynomial time? Because, you need infinite time. Because there is no like gamma. Okay, so one kind of fix for this could be that, you just cut the tree at some place and hope that, now it's finite horizon, maybe the problem is still hard. Okay, but the problem with that is that to maintain linearity, you have to like now give some reward at the leaf nodes, which are not going to be minus 1. It's going to be basically the distance from the S star assignment. So we cannot like simulate those rewards efficiently. If, we cut the tree at some depth. Some finite depth. Okay, so that's the problem. And it's basically saying, like if we forget about this whole thing, we're trying to create like this kind of like some problem, right? Some search on a tree. And we want like information about the solution to not like flow into this graph, right? And the way we kind of design this thing, right now the leaf nodes are giving a lot of information into the tree. So we need these rewards to be like small so that the information is like kind of uniformly hidden everywhere instead of like a lot of information that we cannot handle. Okay, information about the satisfying solution. Because recall, we are on this hypercube, we're roaming around. So we want our reward function to kind of give us less information to make this problem hard. Okay, so I'm going to give the final construction now, but is there any questions up to now? No questions, right? This was...
I have a
Sorry, did you say you have a question?
the Q function.
Mhm.
No, sorry. Somebody said that if the rewards are not random, then there is a linear time algorithm. So
Yeah,
yeah,
yes, yes,
I guess now
exactly.
you will make them random, I guess.
Yes, very okay, I'm very impressed. Nice. Okay, good. So that's a very good question, right? Up till now we haven't even made the rewards randomized. So this is like already pretty easy. So we also need randomization. And this is what's kind of missing. We need like some randomization to kill off. Perfect. Okay, so now I'm just gonna do the final construction. Okay, and to kind of make things simple, I'm only gonna give rewards at the leaves. All right. But leaves might not be at the same level. They could be somewhere in the middle too, right? Okay. And the reward will depend on the assignment and its level, which is all part of the state. So it depends on assignment, right? And its level, right? So a state also holds like level in it. Now, okay, so I'm going to define the reward function. And at the leave, all actions will give the same reward, right? So the reward basically depends on the state. It's 1 with probability 1 minus L plus. Okay, and 0 otherwise. So with this much probability, it gives 1 and 0 otherwise. Okay, and at the leaves, it's not giving any. And so, okay, maybe it's like too many things here, but like the way I'm kind of, this thing, you should think of this as just a function of L plus D S S star. Okay, and it's a degree R polynomial in it, and has the right things we want, as the distance from S star increases, you get less reward. And as the depth increases, you get less reward. Okay. And it's a degree, like you could probably also choose, exponential, say. Okay, maybe this is probably the right way to say it. So I have this function. Okay, so I'm trying to like kind of approximate this exponential function. This is really the function I wanted, but I don't have that many features to kind of approximate it. So I'm just gonna pick, degree R approximation of this function. And that's what I'm picking here. And R is going to be some constant for us. Okay. So my reward function basically gives very small reward. So mostly zeros, right? Except with like this small probability, which decreases as you go down the tree or away from the satisfying assignment. Okay. And it turns out that this dependence on this like L plus D S S star kind of means that, if you look at the V star at any state, so this is even inside the tree. So reward is only 1 on the leaves. But, V star has exactly the same form as the expected reward. So expected reward is just this, this probability. Okay, I mean, to prove this, I need, many things, right? I need to first talk about what is the optimal policy, right? And then why does optimal policy has this reward? But this all follows very similarly to the way we kind of talked about the other thing in the reward -1 thing. Like you have to, the greedy policy is the best one. In this case, also the greedy policy is gonna be the best one. The greedy which goes towards S star as fast as possible, right? So, and then basically, if you kind of do like a little bit of a manipulation, you basically see that V star has the same form as expected one. Okay. Okay, so like I said, R is like some kind of constant for us, right? So this is good. So now V star is linear in D equal to V to the R dimensional features. Okay. Right, because it's a degree R polynomial. Okay, and let's look at what's the reward at the last layer. Because if, we end up somewhere, we finish the game before we reach the last layer, then we actually found the satisfying solution. So that's not the case we care about, because that doesn't happen very often. That happens exponentially weekly. So the reward at the last level, we're going to see is actually at most v to the minus r squared. Okay, so there is like this gap, a non-polynomial gap between the dimension and this reward. Okay, so let me just do this computation. Remember, the expected reward is this much. Okay, and at the end, even if you reach the satisfying solution, this will be like at least h. Okay, and this is all just poly V. So this is just because H also is like big. Okay, because we can choose H to be also V to the R. This is exactly what D is, right? Right. So just because your H can be now the same order as the dimension, you actually get like R squared small error. Okay, so what does that mean? Our dimension, feature dimension, is V to the R. Our horizon is also, H, V to the R. Okay, so, our polynomial time RL algorithm will run for at most poly V to the R time. Okay. And such an algorithm, will visit the last layer, poly V to the R time, right? So it's going to see one, with probability like very, very small, right? Because poly V to the R divided by, V to the, this R squared is basically going to 0 for large V. So you're basically never going to see 1. Otherwise, like very like, so 3/4 of the time, you're never going to see 1. Okay, so that means that we can, even if we replace the reward function with all zeros reward, the same algorithm is going to work. So you can use that to solve, basically said. So that's the construction. It's just this gap between the amount of reward you get and the number of times you can visit the last layer means I can never see 1, and you can just replace his reward function with 0 reward function. Okay, I mean, obviously this is not exactly formal, but this like, just works. Like I just have to write down, more formally, but this is exactly that.
So I think I have one question. So
Perfect.
could you please go back to the place where the reward is defined? The this thing.
Yes.
So here S star is the optimum state, right?
satisfying solution.
Yeah, that's one. So how does one compute this, or do we need
Yeah.
to compute this?
Yeah, so that's exactly what I was trying to say at the end. So that's the you're asking like same problem, right? Like why isn't the same problem there, right? So what I'm trying to say here is like, you can replace the reward function with zero. So say that, I mean, you have a polynomial time algorithm which solves this problem. What I'm gonna do, I'm gonna, instead of simulating the reward by that thing, I'm gonna just simulate by zero. I'm always gonna give you zero. And your algorithm is gonna behave the same, you know, all the time. Like at least, like like it's not gonna beat the probability limit.
I think the thing which is jarring is that we need our algorithm to run on some instance.
Mhm.
So we're saying that we are going to start with a start instance, and we are going to reduce it to an RL instance.
Mhm.
So I guess my question is that what is that RL instance? So I guess what you're saying is that the RL instance is the one where the rewards are really painful to figure out, but then the RL algorithm is just gonna output zero.
Exactly, exactly. So no, algorithm is like there's like an oracle, right? So I'm basically changing the MDP. So there's this another MDP I can create, and your algorithm's output is not going to be different between these two MDPs by more than a constant probability. So for like most of the probability, it's going to be exactly the same. So your algorithm cannot fail on the set either. Yeah, so that's like, do you get it?
I think you could explain it a bit more detail. I think we have time. We have 15 minutes almost. We have 10 minutes, so I think almost.
Okay, okay. I can just open up my paper and that will have all the right notations too.
Oh, okay, sure.
Yeah, because I need more notation here now. Okay. Okay, so this is like basically what I'm trying to do here. Okay, so this is like, I'm saying like if I have this algorithm which uses like this MDP that I was talking about, right? The one with the right reward function. And it runs in like say time VR square over 4. So it takes exponential time, right? Um, and then outputs this policy pi, which succeeds with some probability. So this is like error probability is like should be like 1 minus the success probability. Then if I have the same algorithm run on the simulator, it's going to still run in the same time. And it's going to output a policy which has the same value, but with a slightly different error probability.
Great. And what is the simulator exactly? I think that's the part which I'm not getting.
The simulator is just going to return only zero. Okay, so this is what I mean. I'm exactly so it's like the reward function is only going to return zero, and your algorithm, like your just because like your yeah. So let's see. So your expected reward is basically v to the minus r square over 4, right? This is the computation I just did at the last level, right?
The thing I'm not getting is that if the reward is zero, then how is it? So in the theorem statement, if you just
Yeah.
go, so here,
Right.
how is it that you're getting this b star minus 1/4 when the reward is zero? Like, how is that possible?
So exactly. So it's basically saying that you should not be able to do this in like sub exponential time. So, like, what your algorithm could do is actually just infer the clause, right?
Oh, oh,
And
okay.
infer the transition function and solve it,
Okay, got it. Got it. Yeah.
right?
Okay, got
And
it.
so I'm kind of like enforcing that. I mean, I obviously can't, you know what I mean? Like, yeah, it's
Yeah,
just like
great.
it basically is working on zero reward.
Yeah, yeah. Got it.
Yeah,
Excellent, excellent. Thanks. Awesome. Yeah, now I get it.
yeah.
Questions?
But that was a really good question. I have to explain this, but I always feel like it's I don't know how far to go to explain. So every time I give this talk, I always have somebody who's like, oh, this is jarring to me, and then I go down the path convincing that person at least. And I feel like that like convinces like other 50% of the people. So I'm always happy when somebody asks me this question. So thank you, Jatin. Just a summary of things we have done. So we are done with the proof now, right? Um, and we saw that we can do this like polynomial lower bound, but we can also do exponential lower bound as the RATH, but that one gets a little bit more complicated because we cannot do it for a general SAT instance. So we have to use like this um, somewhat easier version through PCP. But that one is also known to be hard, but just showing that that is a hard instance, still a hard instance, is a little bit tricky. And also we need to um, kind of change the construction a lot. So the problem right now is that, when we build these features and the reward function is only like a um, polynomial of that. So we need it to like actually grow like exponentially fast. And so that requires a lot of changes. Um, anyways, so the summary of like this whole thing is that we cannot solve linear RL efficiently. In other words, linear RL assumption is not enough to justify efficient RL. Okay, and so what this means is that we need better assumptions because in practice things are working, right? So um, what is it in a little bit more natural problem that allows for better algorithms? Okay, and in particular, that's I think is a good open problem is, why can standard RL algorithms solve these like control problems? So what do I mean by control problems? These are the problems from the gymnasium. Library, right? There are these problems like cartpole and mountain car, right? PG algorithms and other algorithms can solve these control problems. So what assumptions do those control problems satisfy? And I think that would be pretty cool if you can show that, there are all these control problems, they have like this specific structure, which is probably a little bit more than linear RL or different than linear RL, which allows for like efficient algorithms.
I guess two almost same questions. So one is that, could you give us the example of the simplest control problem you can think of, for which we don't know?
Cartpole. So cartpole is like super like, simple, right? Like this is what we did in day two. There are four variables and they're even like correlated, like the cart position and its speed. So space is pretty simple. The dynamics are also very simple. But yeah, obviously you cannot write V star, like V star is not, I don't know how to write that. Um, but maybe there's like something else about the problem which makes it easier. Um,
My naive guess would be that going by your construction, which is actually very insightful. I think what it tells me is that the hardness seems to be coming from these transitions. So the actions that you take, and the structure between the states, so the
right.
linkages between the states, that seems to make it very painful because that's what's modeling the SAT formula actually.
Yeah, I guess where the solution lives, right? Like, I mean, I can create the tree pretty cheaply too, but I guess the solution, like the solution where it lives, some of that information is not flowing up from the reward functions or something like that. Is that what you're saying?
Uh, 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 yeah, something like that. I mean,
Yeah.
yeah, maybe the reward function or maybe the actions. Uh,
Yeah. Yeah, they're
so
correlated, I guess, right? Yeah. Right. Yeah, you're right. Yeah. So for example, in cart pole, the states would be like, you are in some place, you apply some force, you go in this direction, right? Those kind of changes. And the reward function is like always high whenever you're close to the zero. So yeah, there's a lot of like access to reward function, high reward function. Yeah. But this is like really hard to like formalize and then kind of generalize also in a way that, it's kind of tells us something more about like other problems too, card pull, mountain car, all of them. Um, but yeah, it's a good start.
okay. Any further questions? Because I think, yeah, we have like 2 more minutes, so we can ask any last questions. I think this is also last talk of this boot camp.
Yeah. So any question about any of the days or in general questions for me? I'm obviously okay with that.
So it's the last few minutes of your access to Gaurav. After that, you will.
No, after that, you can email me, and you don't have to type RL Bootcamp in front. You can email me with any kind of subject. It was fun. It was really fun for me actually because I haven't talked about RL in a long time, and I was like, "Huh, how should I talk about it?" So I got to code a little bit. So I like coding RL and seeing like, oh, my card pull is working. So it was fun for me. I'm assuming hoping like it was also fun for you guys. Uh, and you know, enjoy the Bangalore weather. I'm assuming there's gonna be a lot more fun rest of the days too. So enjoy ICTS. I wish I was there enjoying ICTS.
Yeah, most definitely. Yeah, I think yeah, it would have been great if you could have been here. But hopefully next time or another time. Yeah,
Oh yeah, next time for sure. Next time for sure because yeah, I'll get my yeah. Yeah, perfect.
I think there's one question.
Yeah.
Hello, sir. Hello, sir. I am Shomodeep Nag. Sir, first of all, it was a very amazing experience to be part of this IL bootcamp. Uh,
Oh,
and, sir, may I have your email, please? Actually,
oh, yeah, it should be so that's a good question. How do I type it in here?
sir.
I can share that. Don't worry.
Oh, chat. I
Yeah,
can.
I can share the email. I mean, it's
Okay,
probably
okay,
already
perfect.
somewhere on the web page.
Okay.